So remember, there is this relationship between the function f of x and its derivative. Would anybody, in the simplest possible terms, remind me what is the derivative?
The movement, or like the speed of something?
That's a particular interpretation, so it's instantaneous velocity. Sure, that's a very good one, but slope of a tangent line, Brodman says, yes. Graphically, it's this, guys. If you're an insect that is flying onto a curve, you ask yourself what question? You ask yourself whether or not the curve starts looking like a straight line. Good? If the curve starts to look like a straight line, then the function is differentiable at the point that you were flying to. If it never starts to look like a straight line, then the function is not, the curve is not differentiable locally there. Does it make sense? Very simple. Zoom in. At a point, it looks like a straight line segment, differentiable. If it doesn't, not differentiable. And we covered, we try to explain why when you zoom in at a point, P, you are flying towards it, you will begin to see that it's a straight line if and only if the function is differentiable at the point P. Differentiable meaning that you can calculate some slope between point P and the point Q, which you are sliding towards P. And remember how we try to explain it. The idea is much simpler than it appears. All we do is we are zooming in at the point P, and then we can select arbitrary edges to be our horizon, right? If you're an insect, you can look around and you will be seeing a horizon. As you're zooming in, the left line will be the left edge of the screen and the right line will be the right edge of the screen, which means whatever is past the right line or past the left line is invisible. And so the bouquet of lines, as I call it, will be more and more focused into one line. The slopes of all the lines that I can calculate over this region will be more and more like one slope. Do you understand why? If the derivative exists, that's the idea, because derivative, you are taking limit. What is it that you're doing? When you take limit, you are perfecting it, right? It means that if you haven't finished pushing the point Q towards point P, then if it's close enough, then the slopes are going to be essentially like one slope. The slopes are going to look more and more like one and the same slope, which is the slope of the tangent line. Do you understand this idea, guys? In office hours last class, I spent some time with, and I showed the geometry of that, right? So I showed you how you can figure out certain derivatives purely by geometric means. And if you're interested, you can stay again today and I can show you that the same idea. It's going to be not optional, it will be requirement once we get to logarithms. Okay, so you do want to understand this idea, and the faster you understand it, the better. So then we began considering what it means to be, what's the relationship between differentiability and continuity. Do you remember? So if a function is differentiable, what does it say about whether or not the function is continuous? And what is it that we're even asking? It's a long silence. Has everything spilled, all the water spilled out of the bucket? Is the accumulator empty? Simple question, guys. I have a differentiable function. First of all, what does my statement mean? I have a differentiable function. It means what? Give me a picture. right? If I say I am looking at a zebra, you know, you can give a description. It's something that looks like a horse. It has 4 legs. It has stripes, white and black, right? You give me a description. It's you imagine a zebra, I presume. David Wang, yes, beautiful. When you zoom in at any point of a differentiable curve, you will eventually end up seeing a line. Does the idea make sense, guys? So my picture, I tell you exactly what's my picture of a differentiable curve. It looks to me like a chain of microscopic line segments. Can you see that? The bikini, interesting. Good, guys, you understand? Pavel, you understand, yes? Or what? Or something is not clear?
I'm not gonna lie, I kind of zoned out. I was eating and checking something. So I would just say yes and then catch up as I.
No. Guys, are you alive? Are you awake? Am I screaming out there into the void? Who am I talking to? So, clear or not clear? You have to have this. I'm shoving in this picture into your mind. Do you have it in your mind? Very simple picture. Differentiable curve is built out of line segments. Zoom in anywhere, it looks like a line segment. That's what we picture here. Yes, beautiful. So differentiable curves are they continuous or not? And simply why?
No, it's not continuous because like I would say the graph can look somewhat different. It can look like, this, and it's not really a continuous line at that point. It starts at a peak and then drops down. So it's not a continuous straight line. I don't know, it really depends on the graph and how it looks.
No, I mean, so just a second. So first, guys, when you answer this question, think about 2 things. What does continuity mean? Continuity means that the graph could be drawn without lifting a pen, correct? If the function is continuous everywhere, you can draw it without lifting a pen. Or you can imagine that it means that this is one wire. It's a connected wire. You pull at one end of it, it will pull the entire wire. Yes? So if a function is differentiable, it means locally it looks like a line segment. Does a line segment look like one piece? Does it look like a line segment is torn apart? So differentiability means what? Differentiability means the curve locally looks like a line segment. So it means that everywhere you look, it does not look broken, right? Discontinuous means broken. Continuous means always attached. Everywhere you look, it looks like one whole attached piece that it was drawn with without lifting a pen. So if you zoom in and it looks like a line locally, it means that where it looks like a line, it cannot be broken because that doesn't look like a line. You see that, guys? Do you see my picture, right? It's very clear to me. It should be just as clear to you. Continuity means that the entire thing is connected. Lines look like a connected piece. Okay. So differentiability always means a differentiable function always continuous. Okay. How about continuous? Is continuous always differentiable? Okay, David says no. What about the rest of the class?
I don't understand the question.
You don't? Continuous. You need what is continuous? We know. Does it imply differentiability?
Oh, okay.
In other words, if I know the function is continuous, does it? You see, you understand? I'm asking you to play an animation. Continuous. That means that it's one whole curve, and that means, and differentiable means I zoom in at a particular point of this curve, and it looks like a straight line. So if a function is continuous, does it mean it is also differentiable?
I would think it's not correlated fully. Like it is in some situations, but not in every. So I would say it's not correlated.
That's what we are trying to understand, guys. You see, two things, guys. I mean, it's most likely futile that I mentioned it, but you know, you should not just listen to the lecture and just go home and not open anything. You're supposed to be practicing problems. You're supposed to read and think about it actively. That's how you get to be good at it. So, Christian, you're saying continuous implies differentiable. You understand what you're playing in your mind, right? You zoom in, must look like a line segment. That means differentiable. Continuous means you never see any tearing in this in the fabric of the graph.
If I remember correctly, it's if it's continuous, then it's differentiable. But if it's differentiable, it's not always continuous.
Oh, careful. We said the other way around. We said that if it is differentiable, it's always continuous, and we can easily prove that. Here is a proof, if you recall. So remember, continuous, you can recognize it from a graph as an interrupted whole piece, right? Just zoom in. How do you check continuity? You check that there is no tearing. So zoom in at a point and ask, is there a tearing at that point where you zoomed in? Right? If there is no tearing, it's continuous at that point. Does it make sense? So zoom in on a differentiable curve. So everywhere you zoom in, you eventually start seeing a straight line. A straight line exhibits no tearing. Therefore, it's continuous, right? Differentiable, therefore continuous. Do you see that, guys? You have to understand what you're doing. Why do I remember it? I would not, you see, I would forget most of your names very, very quickly. I already don't know them because your name is arbitrary to me, right? I do not see what's the connection between your personality and your name. But with continuity, the connection is very obvious. It's just very, very simple. Do you understand what it means for something to not have a tear in it? If you understand that, then you understand continuity. Differentiability just means zoom in and you're seeing a straight line segment anywhere where you zoom in. Good? So we can prove that formally. Here is a formal proof, guys. Here is how it works. So we have this limit. This limit is the limit that if it equals to f of a, that means the function is continuous at the point a. That's just formally carrying out the probing. And this limit is the limit that represents the derivative at point a. Yes? So I want to describe this limit that's unknown to me from the hypothesis that I know that the derivative exists. And how do I do that? I begin reshaping this function to look like the derivative. So I can see, I can make the numerator, it will be f of x minus f of a plus f of a. You understand that? That is my payment. I just really want the numerator. And then the next step, I divide and multiply by x minus a. So now this shape is known to me, right? This expression I recognize as the derivative of f at a. This is just a constant, and this is going to 0. So now I know when I take the limit, this is the value of the function at a, the derivative times 0. And that means it's f of a. That's a formal verification that differentiability, it means that this limit exists and equals to f prime a, implies continuity, which I already expected because zooming in at a line means that I'm not going to see any tearing in the fabric. If I see a nice line, there is no tearing. Clear? Right, if you understood, guys. And Brandon, straight lines and circles are naturally differentiable. Line is obviously differentiable, a circle less obviously so, but differentiable, yes. Truly clear, guys. There is, by the way, something relating to mathematics. It possibly is a rant. I'm not sure you would even listen to it. But one thing about how propaganda works, I mentioned that to the morning class. If you speak a bunch of, let's say if you speak Russian, you can see how Russian news present information. You can then compare it to how American news present information. And the interesting thing about any presentation of information is that you can only describe the facts and lead people to wrong conclusions. And one reason for that is people, strangely enough, they think they're not good at abstract reasoning, but they are truly too good at abstract reasoning. In other words, it's not reasoning, they abstract and introduce information that's not there. So for example, you are seeing me on the screen. If you were to describe what shirt am I wearing, well, you see this green shirt over here. But if I stood up, perhaps there is no shirt below that. If I stood up, perhaps there are no legs that I have below. Right? So what you truly see, that's pretty difficult for people to do, is only what's on the screen, without any interpretation. Anyhow, I'm not sure if you understand where I'm going, but I'm just telling you guys, right? So if you can think precisely, you are not so easily misled. You can just listen to people argue and their presentations of information, and you know where it's false when you understand formal reasoning. Now back to this problem. Differentiability implies continuity, but what about the other way around? Does continuity imply differentiability? Can you imagine something there? Alan says no. What about the rest of you? Okay, Minkowski is here, that's good. I was wondering where you are. Okay, good, no. Good. So I want to get over with this, guys. You see, I slowed down because I think I explain it again and again, but you're not practicing it or not thinking about it enough. The answer is obviously no. Here is a simple example why it's no. Here is a continuous curve. Do you agree it's continuous? It's one whole piece, but you zoom in at the peak and you always see that it's very sharp here, right? It never looks like a line. You zoom in, you always are seeing this broken line here. Zoom in here again, you will always see the same thing. It's broken line. So it's sharp. Sharp points are points of non-differentiability. In fact, in differential geometry, you call a differentiable curve smooth. It's pleasant to the touch. You don't cut your hand around it. And here is a graph of a much more dangerously sharp curve. You see why is it more dangerous? It's called a cusp. In this example, the angle stays the same, but here, as I move closer to the point, the tip point is at an angle of 0. You understand? It's extremely sharp here. The angle here is getting narrower and narrower and narrower. And now let's just see how good you are at estimating the derivative from just staring at the screen. I have the point. This point is A, and I select this point. I select point Q to the left of A. What is the slope between this point and that point? What's the slope? Is the slope positive or negative? Do you understand what I'm asking, guys? Here is this point, here is this point. Is the slope positive or negative? Very good. It is positive slope. Now, why is it a positive slope, guys? Because you always look from the left point to the right point and see if moving there causes you to climb. Okay, do you see that? It's like this, right? You select your left point, and then you point with your pen to the right point. If the pen is pointing up, it's positive slope. If the pen is pointing down, it's a negative slope. Yes, make sense? Always look at the point left of the x-axis and compare it to the point right of the x-axis of where you're searching for, right? So then what's going to happen if I slide the point Q closer and closer and closer to the point P, which is this peak? What's going to happen to the limit, to the slope? The slope approaches to what? Right, so what is the slope approaching, guys? I'm sliding the point Q. Can you tell me what is the slope becoming? Where the angle is getting smaller. Here, I'm showing you with my pen. What is the slope becoming? more and more positive. And how much more positive will it become, do you think, if the angle is getting to be 0? You see over here, the slope is not changing. The pen is not tilting. The back end of the pen is not tilting. But here, the back end of the pen is tilting more and more and more. And in particular, it will go to what? If this angle if the angle between the red line and the curve is going to 0, it will go to infinity precisely. Do you understand why infinity? Look at it. The slope of if I take this pen, there is a positive slope. Now I push the tail of the pen. I push the back end of the pen closer to this vertical line. The slope is getting steeper and steeper and steeper, approaching infinity. You understand? Because I'm approaching 0 plus here, and a positive, bigger and bigger vertical displacement, right? It's vertical divided by horizontal. Vertical is getting longer, horizontal is getting shorter and positive. Good. What happens on the other hand if I am holding my point Q on the right? If I hold my point Q on the right, what's going to happen to the slope? Is it first of all positive, negative? And what happens if I push Q closer to point P? P is the peak here. Becoming not less negative. Careful, Christian, right? Look at it. Here is my pen, and I'm pushing the tail up. It's getting negative and more negative, and it's getting to minus infinity. Do you see that? Because what's going to happen if this is my point Q, I slide it, I'm becoming vertical. Because here is my Q. You see, here is my Q. I calculate slope between P and Q. Q is to the right of A, and Q is lower than this peak. So that means that my slope is negative. And as I slide it here, it's going to approach again. We're approaching a line, so it's becoming minus infinity. And then I think we already worked with this. It's supposed to be a review from last class, guys. F of x is 1 minus absolute value of x. Where will this function fail to be differentiable? Let me help you slightly. So you don't want to draw the graph. You can for this very easy function, you can easily draw a graph. But let's see if you can reason your way without drawing anything. What's absolute value of x? Absolute value of x is minus x if x is negative, and it's plus x if x is positive. So my function is really a piecewise function. Do you see that? It's this and that. Are you with me? You understand? I'm trying to train your sonar because you're drawing pictures, but drawing is very, very limited. So I call it a sonar, right? So you are trying to just blindly figure out what slope are we going to have. So what is the shape of the graph 1 plus x? 1 plus x reminds you of what type of graph? It is a line. It is a line, yes? So what's going to be the derivative at any point to the left of 0? If I zoom in, I want you to tell me what's the derivative without any calculation. What's the derivative if I zoom in at this curve to the left of x equals 0? What's going to be the derivative there? David says 1. Christian, well, you're using the derivative in sense of calc 3. Right, which is the tangent line, right? The derivative is the slope of the tangent line, not the actual line. So for x negative, look at it, it's 1 plus x. It has a the slope is right over here. The slope is 1. Without seeing anything, I know the slope is going to be 1, or the derivative is always going to equal to 1 anywhere to the left of 0. Are you with me, guys? Are you with me, James? Are you with me, Nassim? I know some of you are with me. I'm not sure about the rest of you. Yes? what about now? You tell me what happens. What is the function differentiable at any point x to the right of 0? Is my function differentiable? Is my function anywhere to the right of 0? So write in the comments differentiable or not, and tell me why. Yes, and why? Why is more important? Okay, June. And the rest of you guys? You are zooming in anywhere to the right, you're seeing a line. You see a line without zoom. Zoom in on a line, obviously you will continue seeing a line. So the slope, the derivative on the right will be what value? What is the derivative to the right of 0? Exactly, Rachel. So some people are having perfect picture of what's happening. Others, I'm not sure, right? I want to dispel the darkness. It's very simple. If you understand that, a lot of things are just obvious to you. The answer is what, guys? Why do I only hear from one person? It is -1 because that's the slope. You understand? What will be infinity? So if I zoom in at x to the right of 0, it will be aligned 1 minus x, so it will be -1. Okay, zoom in at a line and tell me what's the slope of that line. That's really what you're doing when you do the calculations for the derivative. Yes.
Quick question.
Go ahead.
So shouldn't 1 plus x should also be 1?
Yes.
Should be 1
plus x. The slope is 1. So to the
Oh,
left,
okay.
if you zoom in to the left of 0, the derivative will be 1 because derivative reports the slope of the line that you're seeing. You understand that? That's the picture. You're a tiny ant, or if you prefer, you're a spaceship trying to land on a curve somewhere in space. The curve is huge. If the curve is differentiable, once you land anywhere, you look around and you think, my God, you're walking on a line, right? If you zoomed in anywhere else, it might be looking like you're walking on another line, but it always looks like you're on a line. Okay, and the derivative reports the slope of that line relative to some particular coordinate system. Make sense? So again, I drew you this curve, right? But in this case, drawing is very easy. But you don't need to draw. You can just reason it from the formulas. They're just telling you exactly what is happening there. Good.
Also, wait, I got another question.
Yeah, go ahead.
Can you scroll a little bit back up?
Okay.
Because keep scrolling up. Right here, right? So is affinity, it's plus and minus affinity because it's going is because of the decimals, right? Because of the limit, right?
Because of this, look at it. You see, it's not a line. The curve is folding like this. You see the difference here?
Yeah.
The angles are always the same. So the angle between the angle that the curve makes to the vertical is in this picture, it's the same. You see, no matter how much I approach the peak, the angle is the same. Here, the angle with respect to the vertical is becoming 0. It's the picture is like when I'm pressing my fingers. See that?
Okay.
So what happens is this, right? So in this case, can you see that my my straight line as I approach my target point, my slope is not changing too much. But here, the slope is just it's becoming steeper and steeper and steeper and steeper because my line is becoming more and more vertical.
Okay.
I can imagine a spaceship. You see this point? I'm flying as a spaceship, and imagine that's just a tiny line segment, a very small line segment. And ask yourself, if you're following this curve, you see the spaceship is now becoming vertical. So initially it's flying at an angle like this, obliquely, and then it's leveling up, and it's becoming vertical, right? Your spaceship, your rocket, becomes a vertical rocket, and if it's becoming vertical rocket, you're approaching plus infinity. Whereas if you are flying in here, let's say you're flying backwards, right? Here is your tip of the rocket, so you're flying backwards, and what's happening is that the tip is tilting more and more and more. You see that?
Yeah.
Yeah, that's the problem. Good.
Wait, I got another question.
Go ahead.
Is it really like, can you really call it like affinity because it has a peak? Because I can understand it's getting smaller and smaller and smaller,
Well,
but the lines actually like meet up.
The slope is increasing without bounds, so it's not infinite slope. I'm not sure. That's not what we are saying. We're just saying that as I approach this point, the slope is getting larger and larger without bounds. So the slope is approaching what we say infinity. That's
Okay.
just a wrong word. You see, we say approaching infinity, but what we mean is growing without bounds. So the slope is larger than a million, right? It's larger than a trillion millions eventually, right? It's larger than any number you can think. So that's why we say this plus infinity. Good?
Yeah.
Ready, guys? Okay, cool. I can show you if you want to. I have a book. It's pretty very nice looking book. It's called Physics for Mathematicians. So it obviously employs tons of differential geometry. I mean, I don't know about you. You look at this, it should be right away. Oh my God, I cannot stop reading this. You want to get to the level where you understand it, right? I hope so. You see, you are young. Your brains are still malleable, I hope. So don't waste your time in college. Understand? What most of your classes are nonsense. You know, I know I've taken psychology, almost graduated with a psychology degree. You know why? I mean, from the very beginning, I thought, oh my God, what a stupid class. I could study, 20 minutes before the class, before the exam, and I will get at least 85. Yeah. Nothing interesting is easy, guys. If it's too easy, that means it's not interesting. Here are the former calculations. Okay, so we already know what's going to be the point where we might not have differentiability. That's at 0. So let's see what happens if I approach 0 from the right. It's already clear from here. If I get, no matter how close to 0 I am, my slope is 1. If I am to the right of 0, my slope is -1. So -1 and 1 don't match. You see, it's like this. The derivative doesn't match, so we don't have differentiability at 0. And here is the formal proof. Look at it. If I approach 0 from plus, what's f of x? F of x is 1 minus x. And f of 0 is just 1. Yes? So when I simplify it, it's just minus x over x, and I get slope -1. So the limit from the right is -1. If I carry out the limit from the left, f of x is 1 plus x, -1 over x. So that's x over x, which is 1. So the right limit and the left limit, the right and left limit do not match, which means the function is not differentiable. But this is known as a left differentiable and right differentiable. Okay, because I can calculate the limit from the right and I can calculate the limit from the left. Right and left differentiable means that the curve looks like a broken line locally. If it's right differentiable and left differentiable, you're going to see a broken line. It's going to be sharp. Okay, guys. Here is an example of a curve that has many points of non-differentiability, infinitely many of them. There is a great German word for it. It's zackig. It does look like a zack, right? Zackig. Zackig means, well, like a rake, essentially, right? It has those sharp edges. So at every point where it's sharp, where the function is not pleasant to the touch, that's where it's not differentiable. You have infinitely many of them. You can create a formula for such function. One nice formula will be y equals to, well, f of x equals to the shortest distance from x, where x, well, the shortest distance, sorry, to an integer. So for example, this point is 1/2. What's the closest distance of 1/2 to an integer? It is 1/2. You agree? Now, if it's, let's say, 2.3, the closest distance to an integer is 0.3. So you can see it goes, so the distance of 2.3 is, it's 0.3. 0.4, it's 0.4, all the way and onwards. Good? So can you tell me, or is it going to be a lot of a big task? Can you tell me what is the slope on this edge, for example? Do you see the slope at this edge? If I zoom in anywhere along this edge, what slope will I report? It's a line, right? So it's a line segment. What slope will I report if I zoom anywhere here? Positive, but what exact value will I report it? If this function is shortest distance from x to an integer, what will I report? That's x minus 1. It's just, it's not a slope. I'm asking you slope. It's obviously not one line. There are many lines here. So I'm asking you, what's the slope of any edge here? Any edge here, what's the slope there? And how do you know? Very simply, first of all, do you understand, guys? What's the distance between, let's say, 2.5? Let's say 2. What's the distance between 1.01 and the closest integer? What's the distance? 1.01 and closest integer. What's the distance? Oh, 0.01, but whatever, right? So so you see what happens here. Any point you select over here, the distance is essentially you can take this point to be 0. This point can be the same as 0 because the integer part doesn't matter. All right, so look at it. You move some distance from an integer, you climb by the same distance. That means you move 1/2 units from an integer. How much do you climb? You move 1/2 from an integer. How much do you climb? One half. So what's the slope? 0.5 is the displacement on the x-axis. What's the slope? So the altitude is 1/2, and the horizontal displacement is also 1/2. 1/2 divided by 1/2 is 1. The slope is 1. Do you understand that? Guys, are you processing, right? It's very simple. It's see, just move a little bit. Move a little bit from any integer. An integer, the distance from an integer to the closest integer is obviously 0. Move a little bit from an integer here, and what's going to be the distance you moved is in fact the value of the function, right? So this horizontal line segment is your vertical because the function reports that distance. You agree? Look at it. Where I hold my red marker, that's the distance. How much? So what's the distance? It's just the same. I just make it vertical when I graph it. Yes. I just take that line segment and make it vertical, which means that it's the same displacement vertically as I have horizontally, which means the slope is 1. At any upward moving edge, it's 1. At any leftward moving edge, it's -1. Same thing. Good? Why -1? Because you can go from here to here. That's going to be, you know, the lengths are the same, except it's just negative. Imagination, guys, develop it. Next question is perhaps the most difficult question here. Okay, are you ready? Is your brain cooked, or it's cooked way too early today? Are you ready, guys? Yes? Nassim, you look upset. Upset or what? What's upsetting you?
No, I'm good.
I hope so, right? Guys, don't relax. It's all fun. Take it as what it is, just a game. Okay. My next question, guys. You see the points of discontinuity, diese zackige Punkte, those sharp, those zigzaggy points, right, are somewhat separated from one another. In other words, look at it. If I'm standing at a point of non-differentiability here, I look slightly to the right or slightly to the left, and I am seeing line segments, right? So it looks like if it's not differentiable at one point, it looks like it will be differentiable at a point arbitrarily close to where I'm standing. Are you following me? My question is that always true? You understand? If a function is not differentiable at some point, then it's possibly differentiable very close to that point. Can there be continuous functions that are nowhere differentiable? That means no matter where I look, I will not ever find that I'm watching, that I'm looking at a straight line segment. That's what I'm asking. That's a difficult question. And I'm just asking for your intuition. What do you think? First of all, does my question make sense to you? Yes? So yes means the question makes sense to me, and then to you, and then of course I will repeat as many times as we can. Okay, so what I'm saying is I'm trying to have a picture of continuous functions as opposed to differentiable functions, right? So here is a continuous function that in some places it's not differentiable. Is it the case that if I'm watching a continuous non-differentiable function, it looks like a lot of possibly microscopic line segments attached to each other at sharp angles? You understand? In other words, if I were to be standing at a point of non-differentiability, will I find that looking slightly to the right and slightly to the left, I will be at a point where differentiability does exist? You understand? So here I'm at a peak, but if I move slightly to the right, ever so slightly, I will be seeing a straight line. If I zoom in at a point slightly to the right of this sharp edge or slightly to the left, it looks like I will see a straight line. Is it always the case? So Carolina, great. You're saying you will technically see a straight line before it, so yes. And so do you agree? Do you always see a straight line next to where you're standing? Or somewhere? In other words, most of the points are somewhat, in some sense, differentiable. You see, I can look at the peaks and the valleys, and it's not differentiable there, but everywhere else it will be differentiable. You think so? Don't fall asleep. No? So let's see, everybody said yes. Okay. Well, to me, the answer was, well, it can be many segments. You see, but I'm talking about something somewhat beyond our class, right? I'm talking about real analysis. And something that to me the answer was clear, but only because, do you know where I worked? I worked at, I think I mentioned that already to you last class. I worked at the New York Aquarium, and I think you forget about it. And I mentioned that I worked with sharks. Exactly, that's true. I worked with sharks, and this is how a shark tooth looks like. But you see, if you zoom in at any, you have the big tooth, zoom in at the smaller tooth, it also has teeth, okay? And I mentioned to you, you remember I even played that song, which I guess you already didn't listen. Yeah, so what you have there is, I really like it the way it's in German. Und der Haifisch, der hat Zähne und die trägt er im Gesicht, which is in English, oh, the shark babe has such teeth, dear, and it shows them pearly white. You see, sharks are the opposite of nice, cuddly, pleasant animals, right? They are very not pleasant to the touch. It's like touching sandpaper. And why? Because you have teeth upon teeth upon teeth. Sharks are covered by their scales are even teeth, you know, they are called dermal denticles. So their entire thing is teeth. It's just one giant tooth, and upon each tooth there are more teeth. So this is the function that you right away come up with, which I will, you know, it's you understand precisely what it means in later classes if you take them. But this is what I'm saying. It's actually you take the original tooth function that I just presented, and you superimpose on top of it more teeth, and upon those teeth you superimpose more teeth forever. So it is possible to construct functions that are differentiable nowhere. Nowhere where you look will you ever see a smooth edge. It would look sharp, and then zoom in anywhere, it looks just sharp. You're always ending up on top of one of the teeth, no matter where you zoom in. Do you understand that? You can see some similar shapes. Let's say the von Koch curve is just like that. All right, we spoke about the von Koch curve. I don't remember if you consider it. You see this picture, guys? When you construct it, it's just teeth upon teeth upon teeth. It's just very sharp everywhere. Most functions are not pleasant. They are, you know, they are shark functions. Here is a quick comprehension check. Don't fall, guys. Are you there? Tell me, please. Yes, Pavel. Yes, tell me, please, without doing any calculations, I want you to find the derivative of this function where x is equal to -7. I want it to be done without any calculations. Okay, I'm waiting for everybody, guys. No calculations. Very quick answer if you realize what it is. Yes, good. All right. So I'm hoping that you just did it independently, right? So what's the situation here? This is what? The graph here is a line. And anywhere I zoom in on a line, doesn't matter if it's 7 or -7 or anything there, right? It doesn't matter where you zoom in. That's just where you're zooming in. And the question is, if you zoom in anywhere on a line, what are you going to see? The same line. Yes? And the derivative is just the slope of that same line. Good? And that slope here is clearly 5. Good? Now here is something that can be used if you understand it. So why do we change perspective in more advanced math courses? The derivative is no longer going to be the slope. In fact, we see slopes are somewhat inconvenient because, well, a plane, it's like a two-dimensional line. It has a pitch, and tilt or a yaw, right? So it has two slopes. A plane is described with two slopes, but you have higher dimensional objects there. What's most important, by the way, slope is not very important because of the following feature. Look at it. If I am staring at this line, you're staring at this line, you can describe it in terms of the black coordinate system, the black xy coordinate system, and let's say the line looks like y equal to 1 times x plus 0, right? But if you describe the same line using this green coordinate system, this green coordinate system is parallel to this line. It might have the equation y equal to 0 times x plus 1. Slope here is different number, but you're describing the same line. It's just a matter of switching your perspective. Yes? Are you with me, guys? So slope is not very significant. What's primary for a differential geometer is the object that you're observing. So there is, for a differential geometer, there is only one line. You see, just and all the multitude of lines that you obtain is the result of switching perspective. And this is the idea that I mentioned in my class. It will be important later on when we talk about inverse functions. So perhaps we quickly, it's because, well, so for example, let me quickly give you that example that some of you haven't missed, because have not seen, because you haven't been, you were not coming to office hours. Here, suppose that, so guys, this is where Leibniz notation is kind of useful. So what is the derivative? So if I have, first of all, if I have y equal to x squared, let's do it fast because you know how to do it. What is dy dx? Dy dx is what? Exactly, ratio. It's 2x. We can do it using the definition and it will be 2x. Good? It's 2x. Now suppose that I ask you to find the derivative of y equal to root of x. Okay? You can try doing the definition from scratch, but here is how you can do it using differential geometry, right? Are you ready, guys? So what is y equal to root of x? What does it mean? It means that if my first coordinate is some number, my second coordinate is root of that number. Yes? Are you following? And so I can draw this coordinate system. And here is my my function, this function, right? Now suppose that, so this is my x, this is my y, right? So what I'm interested in is in the derivative. In other words, I can imagine that I have some astronaut making a spacewalk, and he's walking on the x-axis, and he is staring up, and he is located at point x, and he is staring up, and he is observing the tangent line. This is the tangent line that he is observing. The tangent line is given by vertical displacement dy, horizontal displacement dx. Yeah, so he's observing dy dx. He just wants to know what it is. And he can ask help from another astronaut that's walking on the y-axis. This astronaut is staring up at this curve. First of all, what curve is he seeing? What curve is he going to see? Let's observe that. Look at it. The curve is described by second coordinate. So this is supposed to be x here, right? Yeah. So he is seeing what? He is seeing that his horizontal is the y-axis. Are you with me, guys? His horizontal is the y-axis. This astronaut here, his horizontal is the y-axis, his vertical is the x-axis. Now, what is he seeing? He's seeing that that the first coordinate is the square of the second coordinate. So he is reporting the following. He is standing at some point y, and the coordinate that he is seeing is the coordinate that he is seeing is if y is where he is standing, then the x coordinate, the first coordinate, is the square of it. Do you understand this, guys? Very important point here. Do you understand it? That is what this guy is observing by staring up. He's seeing the curve x equal to y squared. That's x equal. So x equal to y squared is what he's seeing. Do you understand that? The most difficult thing, guys, that's what is, do you think, what is theory of relativity? Theory of relativity is describing the same phenomena, but through different perspectives. This is a version of it. Two people are watching the same curve, but their description isn't the same. Do you understand that? It's very, if you understand what the symbols mean, it's pretty obvious, right? So what is x, what is y equals root of x? It means that this guy is watching and he's saying, oh, I am observing the following thing about this curve. I'm observing that that the second coordinate is the square root of the first coordinate. And this guy is describing the same thing differently. He's saying, oh, I'm standing at, this is my horizontal place, and I observe that that the other coordinate is the square of where I'm standing. Understand? The square root, and this is saying this is the square. It's the same description. Do you understand?
So is the red line the red line is the tangent line, right? And
the red line is the tangent line. It's the same line that both of the observers are watching. Both astronauts are seeing the same line, but for astronaut that's walking on the y-axis is his horizontal.
Okay.
Okay. So they are seeing the same curve, but they will describe it differently. So this one is seeing the square function, the parabola, and this one is seeing the root function.
Oh, okay, okay.
Yeah, but they are watching the same thing, but they are reporting it differently. Do you understand?
Because the guy on the y line is seeing the straight line, but the guy on the x is seeing the actual curve.
Well, they're both they're both seeing the same curve and the straight line. That's not my point. Is this here? Look at it. This guy is walking around and he's describing this curve. What is he saying? Okay, if you're he describes this law. If you stand in over some number on a horizontal number, the vertical number is going to be the square root of the horizontal number. That is this description. Do you understand?
Okay.
Don't think of, you see, you're noticing regularity. So if you're standing on a horizontal line, that's what he's saying. I'm standing somewhere on a horizontal line at some number. The vertical value for this curve is the square root of that number that I'm standing over. So for example, if I'm standing at 25, the vertical is for me, the vertical coordinate is for me 5.
Okay.
Right? Now, you understand what I'm trying?
Yeah,
X, you need to, guys, this is language here, right? Nothing more than a language. So this X here is, if you prefer for a moment, it's 25. And then the other coordinate, so that's horizontal. And vertical for him is then 5. Okay? Well, this guy on the y-axis, his horizontal is different than that for the other guy, right? So what is he saying? He's observing something entirely different. He's saying, if I stand at a horizontal point y, I just want to keep them the same letters. If I stand on the horizontal point y, because for him y is the horizontal axis, then my vertical value which is my x value, is the square of the, you see, in other words, this is now my horizontal, and now I'm reporting the other way around. I'm reporting from 5 to 25. You understand? If this is 25 and 5, then this is basically standing at the point 5, and is reporting that the vertical point is at 25. Are you with me? It's extremely simple, guys. It's just a matter of not being confused by the two descriptions. It's very difficult to communicate, right? And that's really why theory of relativity is so difficult, because you are describing the same thing but through different perspectives.
So wouldn't so even so all right, maybe just test this out. So so the guy on the y-axis, right?
Yeah.
He's seeing y squared y, right? Couldn't you say the guy that's seeing the tangent line is also seeing x squared?
So they're seeing the same curve. Let me just try. So what Carolina is saying, I was looking at it. It's good. I just wanted to keep the coordinates in the same way I did before, right? So if you say horizontal coordinate and vertical coordinate, then I just don't want to. I want them to keep the same notation. You see, the first coordinate here, the y squared, is his vertical coordinate.
Okay.
This guy, it is the vertical coordinate, and the second is his horizontal coordinate. I just kept them, which is, again, it's confusing one way or another. Again, you understand that this point here, for let's label this green guy number 2. Green guy number 2. He is number 2 green guy, right? So for green guy number 2, this point is his vertical, and this point here is his horizontal. Yes. Whereas for this guy, green guy number 1, it's the other way around, right? Horizontal is 25. Good. Are you with me? You follow it?
Yeah.
It's much simpler than whatever we have there. Do you understand? So what is the slope that, so they can communicate about the slope. So for this guy, you can calculate the slope at position y. For him, the slope is simply dx over dy. All right. So this guy, the vertical guy, I mean, the guy on the y-axis, he will communicate the slope as 1 second. You will communicate the slope as dx over dy. Yes, and dx over dy is simply 2 times y. Because what does it mean? All this, when you say the derivative of x squared is 2x, what you're really saying is this: if I stand at a horizontal point x, the derivative, the slope will be twice that point. You understand? Don't look at the x yet. At the horizontal point where I stand, the derivative is twice the horizontal point. That's what I mean. Don't read the letters, read the meaning. Okay. The slope is what? If I stand at some point on my horizontal, my slope will be twice the horizontal point, right?
Yes.
So dx dy is 2 times y. That's what it is in symbols, yes? So then if that is the case, what will the guy with the red coordinates report? What would be his slope? So he is reporting dy dx, because for him, dy represents the vertical, dx represents the horizontal. He will report what slope? They're talking about the same point. So 2y is that point, what he will report.
Wouldn't it be 5?
Slope wise. And can you do that in terms of the 2y symbol, guys? You see, if you stay after class, I will teach you to think of it better. What slope will report? Look at it. This is the same. The point. This is the slope. So what would he report? Almost, Carolina. Almost. He will. What is dy dx? It is the same as 1 divided by dx dy, which is 1 over 2y. He reports the slope 1 over 2y, but it's not polite to report it in terms of the vertical coordinate. I want to report it in terms of horizontal coordinate. What is y? Y is root of x. So the answer is 1 over 2 root x. Do you understand? It's the same. The formulas look to you like two different things, but they're exactly, you're talking about the same derivative. You're talking about the same curve. You understand what I'm telling you guys? Isn't it cool? It's not in your textbook, but it is in differential. But it is the thinking that you develop for differential geometry. It ends up much more difficult than what I present here. Okay, and the reason, if you are not understanding it and if you feel confused, the reason you're feeling confused because you see you are paying attention to the symbols and not to the meaning. Okay, just you have to imagine you are the second guy and ask yourself, what is slope? Slope is vertical divided by horizontal. What sort of curve am I seeing? I'm seeing the square curve, right? It means my vertical coordinate, vertical meaning the x coordinate, is the square of my horizontal coordinate, right? So I know already how to do the derivatives. It means that at the point I'm standing, my slope is twice that point. And then you relay that information to the guy on the x-axis, and then he right away knows what is the slope for him. The slope for him is 1 divided by the slope that was computed by guy number 2. And then he converts this information in terms of the x coordinate. That's all it is. Good. Let's go back to the board. And that's what, so this is a very useful idea. In other words, if you understand it, this is what I try to describe here. If you understand it, you have far fewer functions that you deal with. In other words, it looks to you like there is x squared and root, it's the same function. And far more than that. All right, here is the last exercise from this particular section. Please draw me, or just if it is in the notes, please tell me what is the graph of y prime here, of f prime here, right? So what's the graph of the derivative of this curve? If this is f of x, what's the graph? Yeah, it's pretty simple here because look at it. You can zoom in anywhere in here. You're zooming in on a line, right? So that means that you will have the same values. Guys, if you're confused by something, don't overcome your laziness. Stay after class. We can discuss what you're confused in very great detail. Do you understand what I asked you to do for this example? Here is the curve y equals f of x. Find or draw the graph of the derivative. You can even label it because it's very simple to do it. What's the graph of the derivative?
Curve of y equals fx?
Sorry?
That's the curve of y equals fx?
Yeah, that's the graph. Now, what if that's the graph of f of x? What's the graph of the derivative? That's very good, June. A good way of reporting it. Fine. Graph means that you're only you're checking what slopes do you have, right? So let's say I am a small fly. I zoom in at this point here. What slope do I report? If I zoom in at this point, what slope do I report? If I zoom in at this point, what slope do I report? What about here? What about here? Right? So because it's made of line segments, there are not many slopes I can report. Correct? So yes, you can tell me what slopes will be reported. And so James, you say 3, 0, minus 3, but be careful. Is that the slope that you report here? How do you calculate the slope? You take one endpoint and take another and then see what are the coordinates of this point, what are the coordinates of that point, and then calculate the slopes using those coordinates.
Yeah, but that would still be since it's going up to 3, it would still be x plus 3 because it's still going up to 3.
Well, let's see. What is this coordinate here? The
Oh no,
coordinate,
that's 0, 0.
and what's the coordinate here?
That's 3, 3.
Exactly. What's the slope? So you have
That's
vertical minus initial vertical,
That is
horizontal minus initial vertical, right?
okay.
Yes.
Yes.
So professor, would the graph kind of like look like a staircase almost?
Yes. It looks like some sort of staircase. It's a step function. Okay. Ready, guys? Let me do it fast because I need to move on. Well, yes, Christian, I see the function, but you're already in Calc 3 mood, right? Just tell me the slopes, right? When you take the derivative, you're giving me slopes. It's not how we understand it, right? So Carolina, beautiful, correct. Okay, so I'm gonna just speak about it, guys, right? I want to move. Here is what it is, right? So between 0 and 3, the slope is 1. I know the slope is 1. You see, why is the slope 1? Because I know this point. You see, I see a straight line segment, and this point is 0, 0, and this point is 3, 3. Right? So vertical displacement is 3 units. Horizontal displacement is 3 units. 3 divided over 3 is 1. So the slope here is 1. Now here, the slope can be obtained. It's first of all horizontal. Horizontal has 0 slope. Now look at it. What is the coordinate of that point? Here, I'll do it for this point, let's say, guys. What's the coordinate here? The coordinate here is 3, 3. And what's the coordinate here? It's 6, 3. So what's the slope? What slope do we calculate? We calculate the slope 3 minus 3. That's the displacement vertically, divided by 6 minus 3, which is 0. So the slope anywhere along this line, it's 0. You see that? Now, what about this final slope here? Now here, the point is 6, 3. This point here is 9, 0. So the slope is obtained by having y2 minus y1, in other words, 0 minus 3, divided by 9 minus 6. So the slope is minus 3 divided by 3, which is minus 1. Very simple, yes? Okay, so that's the graph. And I mean, I made it go after 9 to be horizontal, so it goes to be 0. And you can see where the line is broken, that's where we fail to have differentiability, right? So you have this type of picture. Good? In general, guys, if you're dealing with a more complicated curve, what do you imagine? You imagine that this more complicated curve is built out of many line segments. And the line segments are tiny as you possibly can, and then you roughly estimate what is the slope. Look at it. Don't pay attention to the x or y axis; they don't matter here. So what you do is this. You see, guys, from this point to that point, the slope is positive, right? And then it looks like the slope is getting less and less positive. Do you see that? So this green line indicates that this is the slope. The slope is less and less and less positive until somewhere around this point, the slope is 0. Yes, move further and the slope becomes negative until somewhere in here it reaches again 0, and then it becomes positive, very positive, and afterwards somewhere over here it's already 0 again. So it has to go positive, very high, very, very steep, somewhere in here maybe steepest point, and then quickly descend to 0. Afterwards, after this point here, it is negative. You can see that you're leaning back. So that's roughly the graph. I don't know how high or low it is because I need to then actually calculate the slopes of those line segments. But that's a sketch of the derivative graph giving information about the original function. Okay, I used to ask questions like that on the exam. We will see if I'll ask it for your exam. Definitely you should look at previous exams that I have posted on my website. Good. Let's move to the next lecture. Derivatives of polynomials and exponential functions. So let's remember, a polynomial is a function that only utilizes addition and multiplication. And here is a function that clearly utilizes only addition and multiplication. I can expand and rearrange the terms so that I can see that here I have the input was not used at all. Here the input was used once. Here the input was used multiplied by itself twice, 3 times, and etc. You see? So I can always rearrange any operation that only used multiplication and addition into one that looks like this. You see, I just group it based on how many times do I multiply by x. So that means that any polynomial can be brought to this form. That's why it can be brought to that form. It's only addition and multiplication, and that will be a presentation of that polynomial. So quick question, guys. F of x equal to a constant. Let's say f of x equal to 5. Is that a polynomial? Remember what it means for a polynomial, guys. A polynomial means that you are expressing this function, but with using only and at most addition and multiplication. It doesn't mean you have to multiply by something, right? It only means that you are using addition and multiplication. Can you express f of x equal to 5 by just using operations of addition and multiplication or not using them? Naturally, you can, right? So the answer is obviously that it's a polynomial. And also from this form, you just set a0 equal to 5 and all the other a's equal to 0. Yes? So it's a polynomial. What is the derivative of this function? Do it without any calculations, please. Right away, you should tell me the derivative. Why is it 0? F of x equal to a constant means that if you graph it, you're going to generate a horizontal line. You agree? Let's say 5 at this x, 5 at that x, 5 at that x. You're just tracing a horizontal line. Yes? So the derivative is right away 0. Derivative of a constant is 0 because the slope of a horizontal line is 0. Very simple. What about this function, guys? What is the derivative of f of x equal to x? You don't need any calculation for that. What's the derivative? Yes, it is 1 because it's x is a line that has slope 1. So everywhere I look, it has the same slope. That's a feature of the derivative. Notice that if you find that everywhere you look, the slope is the same. Again, you imagine a differentiable curve to be a chain of line segments. Yes. So if the slope of all the line segments are the same, they're all perfectly aligned and they are forming one straight line, one global line. Yes. So if you find that derivative is constant, you are looking at a straight line. That's pretty obvious based on what my description here. Do you agree? I hope so. This is doing that in terms of the limit. Now, for x squared, you already know how to do that, right? For x squared, you cannot no longer, you cannot easily tell what it is geometrically, so you carry out the definition. So you cross away z minus x. So now it's limit of z plus x, and that's 2x. We did it many times already. Good? Next task is, guys, can you figure out what is the derivative for x cubed? How do we figure it out? Well, let's see, right? Here is the limit that you need to consider. Z cubed minus x cubed over z minus x. So how do you factor out a difference of cubes? That's the next question. Good? Right. I'm not gonna wait for this question. Let's actually do it together. You see, so let's say you don't know how to factor it, you can use long division. Do you remember long division? So here is z cubed minus x cubed, you divide by z minus x. So then the way you do it, you ask yourself, by what value must I multiply z minus x? Z minus x, by what value do I multiply it to get z cubed? Clearly by z squared. So I need to multiply it by z squared. If I multiply it, so I put a z squared over here, I multiply and I subtract. So this z squared times z will be z cubed. Z squared times minus x will be minus x z squared. Subtracting, I get x z squared minus x cubed. So the next thing I ask, by what do I multiply z minus x? Yes, Nassim, what do you want to say?
How about if we don't use long division? How about if we factorize it in the set?
If you know how to factorize it, that's beautiful. That's all we need to do, right? We just need to figure out how to factor difference of n cubes. And I'm just trying to show what you do if you don't know or don't remember it. You're trying to get to the pattern here, right? So then I'm here at this line, xz squared minus x cubed. So what do I multiply z minus x to get xz squared? Clearly by xz. So I put a xz here, I multiply, I subtract, I carry this operation until I get 0. And I see that the factor is as following, right? It's z minus x times z squared plus xz plus x squared. That's my factored form. That's my that's how I factor difference of cubes. Notice that I have z to the power of 2, and then we have z to the power of 1, and then z to the power of 0. And the power of x plus the power of z always equals to 2, which is 1 unit less than 3. Now, what is the limit? The limit as z goes to x of z squared xz plus x squared, they're all going to be x squared, x squared, x squared. So it's 3x squared. Good? Now, to find the derivative of x to the fourth, you can actually just do, you need to factor out z to the 4 minus x to the 4. You can actually carry out, it's easier than z cubed, I think. You can carry out factorization of difference of squares twice and obtain it this way. Or you can do the same strategy, right? You can use long division and you find out that the z minus x times z cubed plus xz squared plus x squared z plus x cubed will be the remaining term. So that means that when you take this limit, this is what you get. Yes, guys? This is what you get. You cross away z minus x, and then you have z cubed, xz squared, x squared z, x cubed. You see that z is reduced 1 power at a time until there is no more z. And it gives those powers to x. So each of the summands is going to, in the limit when z goes to x, equal to x cubed. So it's 4x cubed is our derivative. Are you beginning to observe the pattern? The question is, how do I factor out z to the n minus x to the n? And here, Alisa Ruvinov, here is what this reminds me of, right? It's basically many interesting things in mathematics are codes for a story. So I hope you listen to this short 13-minute story by Oscar Wilde, The Nightingale and the Rose. Yes? So did you listen to it? If you haven't listened to it, you should listen to it again, guys, right? So I look at this line and I right away remember that story. Because what's happening here is the following. So when you factor out z to the n minus x to the n, it's z minus x, parentheses, z to the power of n minus 1. Most stories have an alpha ending. So
Go figure.
So this z to the power of n minus 1, look at it, that's z, this z is my nightingale. And this nightingale, it's giving its powers 1 by 1 power at a time to x. X is the rose. If you remember that story, the nightingale would sing to the rose, and it would bleed to make this rose turn red. Yes, guys, are you with me? So the nightingale would give its powers, look at it, one by one, and here the rose is getting red. Until there is no more nightingale, it is dead. Yes? So that is, this line is the summary of that story. That's been, in other words, I look at this line and I see right away that same story. Then, and do you know the other part? Who is that nightingale? If you listen to the story, the nightingale bled for a student. Yes.
The
Yes.
the girl in the story, she was she's an interesting person, I guess.
Is she?
Yeah. No, she basically said well you gave me the he got the rose, gave it to her, and then she's like, I don't want this rose. Why didn't you give me pearls? And I'm just sitting here listening to. I'm like, oh, okay. And then she was like, you don't have no silver on your shoes. I guess that was the new Jordans back in the day. And
That's exactly right. You say what is it? I'm not saying she's a gold digger, but she's not messing with no broke. Essentially, that is the
yeah, that's
exactly right. But I was more focused on the nightingale because that's what I am. I'm screaming and losing my voice to you, and you look at me with your indifference in full eyes. And I'm already close to my death, very close. You know, I'm looking into your cold eyes. It's an exercise in futility. I hope you will prove me wrong, but the hope is dying. So again, do you understand what it is, guys, right? And why is it not boring to me? First of all, it's very common in mathematics that you know, you can solve a formula because you realize what it talks about. That's called combinatorial analysis, for example, or they call it a combinatorial story. Okay, so if you look at a formula and realize it encodes a particular situation. So for example, imagine you have a very, very complicated formula, and you realize that it describes how two girls are deciding if they should buy red shoes or blue shoes, right? And then you realize that the solution is that they decided to buy blue shoes, and that will translate to the solution to the formula. Okay, so you can the girls that talk about shoes can tell you how to solve an abstract mathematical formula, or the other way around, the formula can tell you what the girls will do. So each of them by separately is not interesting, but in combination, this unity is very, very pleasing. So this line is pretty much right away. I see the nightingale, right? Because you can see the powers are given to x one by one. So for instance, if I factor z to the 6 minus x to the 6, that is z to the 1 power less z to the 5. Next it will be z to the 4, and there is 1x. Next it's z cubed, and there are 2 x's. Z squared and 3 x's. You see the numbers always add up to 5 in the powers, right? But z is losing the powers until z is gone. How many terms are we adding? We're adding from 0x to 5x. So we have 6 additions in total. 6 additions in total. So the answer is 6x to the power of 5 if I take the limit. Okay? Are you with me? Yeah. The other thing that it reminds me of is the parrot Yossi. If you speak Hebrew, I can show you what it is. Or if you care to know what it is, I can possibly show it to you. Minkowski, do you speak Hebrew? How well? The parrot Yossi. It's a very beautiful song. It says, "I'll buy me a parrot and I'll name him Yossi, and with him I will talk about what no one will hear." Right? And it says, "And you know, parrot Yossi, sadness like wine is she in right, like a glass is she in her bitter wine." And there is one line that says, "With a voice of a poet whose heart is rage and fire among sinful and indifferent hearts." And when you stare at me with bored faces, that's exactly what I think. If you want to listen to it, I'll play it afterwards. If anybody cares. So it's in Hebrew, so I don't know if you would like it or not, but Hebrew, if you don't understand, it might sound like an ugly language. Most languages, when you don't understand them, possibly sound ugly, right? German, do you think German sounds like a very pretty language? Does anybody think German is very pretty? Oh, aggressive. You see, I can tell you what I hear when I listen to German. You know how you tell your girl that you love her? Ich liebe dich, mein Schatz. German sounds, you know, I lived in Jerusalem, and it's when the sun sets, you would see crows. They're flying all over. And the crows, when we hear German, I always imagine that I now understand the language of the crows. I know what they are speaking about. Yeah, German, that's how it sounds. How long to learn Russian? I will help you learn if that's what you want, and I can tell you how you pick up another language. There are some. I didn't send you this video. I'm not sure if it's interesting to you, but you can learn actually if you are dedicated. If you have a reason to learn it, you will learn fast. If you don't have a reason, it will be difficult. Okay. But yeah, that's another thing I can show you because YouTube recommends people that learn some languages. I always like when people learn a language, not because they have ancestry or some other reason like that, but just because something drew them, something rather random. They are more interesting to me right away. Yeah, so I'll show you about that if you're interested. I can tell you that as well. Yeah, so we can talk about afterwards. If you stay with me, guys, afterwards I will talk about language learning, right? And mathematics and anything you like. So very quickly, here is, let's just finish this one idea, and yes, and then we can talk about something else. And if you want to hear that song afterwards, you let me know. I don't want to torture anybody if they don't. So here is, once you notice the pattern, if you understand what the pattern is, then it's very easy to prove that it always holds. Because if S is this z to the n minus 1 plus x to the z n minus 2 plus all the way to x to the n minus 1, all I do is multiply by z, s, and I multiply by xs. And when I subtract, I will get that z times s minus x times s, which in factored form is z minus x times s, is z to the n minus x to the n. And that immediately gives me this power rule, is that the derivative of x to any positive integer is the positive integer dropped, x to the n minus 1, the integer less than that. So in other words, I do this calculation once. So I factor z to the n minus x to the n. And I have this, this is what survives once I do the cancellation. All I have to take a note is how many additions do I carry out. So look at it. I have x to the 0 power. all the way to x to the n minus 1 power. So that means we have n minus 1 plus this extra 0, 1. So there are n summons, which means that when I push the limit, each of them becomes x to the n minus 1 multiplied by n. The gist of that is that the derivative of x to the 6 is 6x to the 6 minus 1. Okay, it's this thing. The derivative of x to the 101, it's 101 x to the 100. I can calculate very, very easy. Yeah. I don't need to go through this annoying procedure of doing the derivative by definition. All right. So to finish off, how do we take derivatives of polynomials? We just need to know the derivative of constant times the function rule and the derivative of the sum rule. And of course, derivative of a difference follows from those two immediately. So I will, today we're running out of time, and I'm sure you're pretty tired, right? Am I right? I cooked your brains, so, you know, but we're not going to leave too quickly, right? We're going to rest a little, and then we're going to do more exercises, I'm thinking, right? We'll see afterwards. I bet all of you disappear. Goodbye, have a good weekend, right? We'll check that. We'll see if you have what it takes in your heart. All right. So I will talk about why this is true in the next lecture, because I figure we're too tired of the symbols. Let's just understand what it means to take the derivative of a polynomial very quickly, right? Derivative of a sum is the sum of the derivatives. Derivative of constant is 0. Derivative of constant times the function is constant times the derivative of the function. So look at it. I take the derivative of this polynomial. It ends up being derivative of 3, derivative of minus 5 times x, derivative of 8 times x cubed, derivative of 10 times it's a 10 times derivative of x to the 4. Yes, it's what I'm reading this. I'm just reading what this line is, guys. Yes. In other words, the derivative is once you know this rule, it's very simple to carry it out. You see, I just take derivative of each piece separately. That follows. I will talk about it next class. I will recount those statements. Good, guys. This is then what we have as our answer. Make sense? Just to be sure, very quickly without any complicated procedure. Tell me what's the derivative of this function. Yes, that's good, David. That's right, Rachel. Yeah, good. That's exactly correct. That's exactly correct. So for the lecture, so I mean, what I imagine we can do is we can take a short pause. Maybe we can talk about whatever you let me know, so I don't torture you with whatever music. I just figure music is part of my idea of how you improve your imagination. I can show you. That's actually something I worry about showing. I can show you my favorite poem or my favorite song. It's in Hebrew, one of them, right? And see if you can understand it if somebody speaks it. Or we can do something in Russian, or we can talk about something else, about languages, okay? So guys, if you are not staying, goodbye, have a good one. And if you are staying, we will just rest very shortly, and then afterwards do exercises if you would like them, or answer questions if you have them, okay? Take care, guys.